In the name of the Almighty, the compassionate, the merciful. This is, in fact, is our last lesson in our course of Mathematics 1, which comprise all the subjects of differential and integral calculus. This course, this lesson, actually, we're going to talk about in this lesson about the fundamental theorem. And this fundamental theorem, in fact, is what is usually remains in the minds of our students. Usually our students, when they pass their study in engineering during the different phases, during their study, I mean during the many years they stay studying engineering, they usually when they speak about mathematics, or when they are using mathematics, the most used actually theorem, which they use it on and off all the time, is really the fundamental theorem of calculus. And this fundamental theorem was in fact first proved by Newton and Leibniz, and then it has gone into many variations. For example, as we said, Cauchy find a new version of it, a different version in which f may not be continuous, etc. And then came Riemann. But this fundamental theorem remains one of the most important theorems in mathematics, not alone, let alone in calculus. In this fundamental theorem, we're going to speak about the theorem itself, and then we're going to find a variation of this theorem when we have a function which is not defined over a closed bounded interval. And again, there are some applications we are going to show either in area or solids or surface of revolution. Now, for the fundamental theorem, we usually teach the second part of the theorem. In fact, the fundamental theorem comprises two parts. The first part, it says the following: if f is integrable in the closed interval ab, the function f of a, which is the integral from a to x f of t dt, is continuous. But if f is also continuous, and this is the Newton, in fact, the Newton result, and then f of a is differentiable, and the derivative of f of x is equal to f of x. And we have seen this with Newton when he differentiated the area in order to obtain the function. So if f is integrable, f of a is continuous, and if f is continuous, then this f of a is differentiable, meaning that this integral is the antiderivative of the function f. In other words, every continuous function have at least one antiderivative. For instance, f, this function here, this function is defined on a closed interval, and it's integrable. It's integrable according to Riemann, yet it is not neither continuous nor it has an antiderivative, and yet it's integrable. Since it's integrable, then the integral from -1 to x of f of t dt it must be continuous. In fact, -1 plus mod x, which is the integral, is continuous for values of x greater than or equal to -1. For example, for this exercise, square root of 1 plus t square or 1 plus x square, this is a continuous function for all values of t. For this function, since it's continuous, then the integral must be a differentiable function. So in fact, if you calculate the derivative, you will find equal to square root of 1 plus x square. Since the function is continuous, thus you can differentiate this because it is differentiable, the integral is differentiable, and therefore you can apply the first fundamental theorem. Now, there is the second theorem, which is the more important. I mean, not the more important, but I mean the one which is more used. The second theorem tells you that if f is continuous, then the integral from a to x to f of t dt is equal to antiderivative of f, small f, substituted by at x minus the same value, the antiderivative substituted for at a. And this is necessary. This is according or provided that f prime of x equal to f x. In other words, that capital F is as antiderivative of small f. In other words, this is a both necessary and sufficient condition for the application of this theorem. So all you have to do is that if you wish to calculate an integral of a continuous function, then all you have to do is that, and this is Newton theorem, all you have to do is that you calculate the antiderivative of small f, and then you substitute for f, for capital F, for the upper limit minus the value at the lower limit. limit. And of course, if you release the value of x, you put instead x, you put b, the same thing. You get this is the most famous, actually one of the most famous theorems in calculus. And in fact, and this is why we call it the fundamental theorem in calculus. And it tells you that the integral of f of a continuous function f over the closed interval ab is equal to the antiderivative of f, which is capital F of small f, and you substitute for the upper limit minus the lower limit. For example, this function here is continuous for values of x greater than equal to minus 4 over 3. And therefore, it is continuous from minus 1 to 3. Since it's continuous, all you have to do is to search for an antiderivative. This is the antiderivative, and directly your integral becomes equal. This is the antiderivative of f, capital F, and you substitute for from minus 1 to 3. In other words, you substitute for 3 minus the value at f minus 1, and you get directly your result here. And this result, in fact, represents what? The area beneath the graph, which is y is equal to 1 divided by the square root of 3x plus 4. Evaluate the ln mod x. Here, this is this function. In fact, you can't calculate the antiderivative except through integration by parts. But what is new here is that there is no need to evaluate the antiderivative till the end. I mean, in other words, you don't have to go till the end to calculate the antiderivative of such function and then to substitute for the limit of integration. All you have to do is that you may directly apply your limits. In other words, you may substitute for the limits of integration directly from the first result of the integration by parts. So the integral of this equal to x ln mod x minus the integral from minus 1 to 2, minus 2 to 1 to x over 1 over x dx. And this here, this limit here, you may say directly this is equal to what? The value of this expression at minus 1, which is equal to 0, minus the value at minus 2, which is 2 ln 2, minus the value at 1. This function here is square root of 1 minus x squared, again from 0 to 1. You may this function is continuous, and therefore you can apply the fundamental theorem. But what's important, instead again of calculating the antiderivative, and we saw this before, antiderivative of such function is easy. You just substitute x is equal to sine theta, and you carry on your integration to find your indefinite integral, and then you substitute at the end for the limit of integration. But there is no point of doing that, because once you choose a particular substitution, which is x is equal to sine theta, you may go along directly and you substitute for theta as well. Since the integral is from x equal to 0 to x is equal to 1, and x is equal to sine theta, therefore you may substitute for x equal to 0. When x is equal to 0, from here theta is equal to 0, and when x is equal to 1, theta is equal to pi by 2, and you directly obtain an integral in which the limits of integration are function of theta. And cosine square theta, you may transform it into a double angle, and you carry on the integration, which is simple, and you finally obtain pi over 4. So there is no point to obtaining the integral at the end, the indefinite integral, which is the antiderivative, and then substitute for the limits of integration. And in fact, this is equal to a quarter of the area of the circle of radius 1 and center of the origin. This function here is a continuous function. It is subject to two rules: 1 over x squared from greater to equal to half and less than 1, while as it's equal to square root of x for greater than 1 in less than 2. This function is continuous, and the first fundamental tells you that if the function is continuous, then the integral of the function from a to x is a differentiable function. In other words, that there exists an antiderivative for this function. There must exist, since f is continuous, and therefore you have two options. Either you carry on the integrator from half to 1, which the student do, from half till 1, plus the integral of the second rule here, square root of x from 1 to 2, or you may you may try to find an antiderivative for the whole function f of x, and it must exist since f is continuous. And in fact, we try to find an antiderivative of small f, and this antiderivative is capital F here, and it is continuous, and you find here that this function is differentiable, and in fact it is smooth. And once this is the antiderivative, so all you have to do for the integral, you substitute for f, capital F at the point 2 minus capital F, which is the antiderivative at half, and you obtain the value of the your integral, which again represent the area under the graph. Second method, of course, as I said, you may decompose the integral into two parts, and you reach the same result. again, evaluate the integral from 0 to 2. Here you have a rule, but there is a problem here. This function is not continuous. So because it's not continuous, then you may not be able to calculate an antiderivative. It's not like the functions of Cauchy. No, this function is not. You may not calculate an antiderivative, and therefore what you do is that you can carry then the integral, and here is your function from 0 to 1. Then you carry the integral from 1 to 2. This is the first rule, and this is the second rule. Now there is one point of concern here, is that in the second portion, which is on the closed interval from 1 to 2, your function is continuous, and therefore you may apply the fundamental theorem. But on your first portion from 0 to 1, your function is not continuous. But you know very well that this function, since it has this value here, which is equal apparently to 1, I'm not sure you have to substitute for 1 in your second rule, doesn't matter. This function here, in the first part of this function, since it's not continuous, then you may not apply the fundamental theorem. But what you can do, since the integral exists, because in this part of the function, which is 1 plus x, the function is integrable. Why? Because it is continuous except at some finite value of discontinuity, some point of discontinuity, which is equal to 1. So there is one point of discontinuity, and therefore this function, the integral, it's integrable according to Riemann. And since it's integrable, if you can put it in a way such that it's continuous on a closed interval, therefore you may apply the fundamental theorem. So what we did actually, instead of giving it the value, it has a limit is equal to 2. You may assign a value equal to 2, because in fact this, if you assign the value of the function at 1 of the first rule given to 7 or to 1 or to 0, it doesn't matter. It's still integrable, and the result is the same. So you might as well, to make it continuous, you may give it a value. You may give it a value equal to the limit of 1 plus x when x tends to 1, which is 2. And therefore, if you give it the value 2, it means that your function is continuous on the closed interval from 0 to 1. And since it's continuous on the closed interval from 0 to 1, then you can apply the fundamental theorem. So your integral is equal to the integral from 0 to 1 of 1 plus x plus the integral from 1 to 2. In fact, this is how the students do. But the reason, now we explain the reason. The reason is that in this part, the function is integrable because it's continuous on this closed interval, whereas here we can make it, it's integrable, but it's not continuous. We can make it continuous to apply the fundamental theorem, because the fundamental theorem applies to continuous function over closed intervals. Now, sometimes the functions, Riemann integral, in fact, apply to functions which are, as I said before, bounded and continuous except at finite number of discontinuities, but they have to be bounded. So if these functions are not bounded, for example, or if the interval at which one carry on the integration has to be, again, closed and bounded. If it is not closed and bounded according to Riemann, then you may resort to what is known as improper integrals. It's like, for example, you wish to calculate the sum of the series 1 plus 1 half plus 1 over 4 plus etc. This series, yet it is convergent. If you leave it to a computer to calculate it, you may come after a month and you see still he calculates. But there is one thing: you don't find a difference between what you find now and what you find after a month. Why? Because it's converged. The partial sum converged. So in fact, the same thing with the improper integrals. If the limit exists of some kind of sum, then we say that the improper integral exists and converged. And actually, the improper integrals is another discovery of Cauchy. And Cauchy consider these integrals, either they are integrals defined on indefinite intervals or integrals in which the functions are bounded. So what we do to tackle these kind of integrals, for example, if you have an f from x into 1 over x squared, this function is, as a matter of fact, is continuous over the interval from 1 to infinity, on the closed interval from 1 to infinity, and you wish to integrate this function. But there is one thing: the limit of integration is unbounded here. Here you have an infinite closed interval, unbounded, so you may define the f over the closed interval from 1 to c first. In other words, you integrate from 1 to c, and of 1 over x squared dx, and this integral exists because 1 over x squared is continuous from over the closed interval from 1 to c. And in order to get your integral, all you have to do is take the limit where c tends to infinity. So if this gives you a number, if this leads to the limit exists, therefore you say that your improper integral converges. So in this case, for example, here, first of all, we integrate from 1 to c to obtain from the antiderivative of minus 1 over x, and you substitute from 1 to c, you get 1 minus 1 over c. And then when you take the integral now, in this case, become the limit, if it exists, of your integral from 1 to c in order to obtain your integral from 1 to infinity. And you find doubt is equal to 1. Therefore, your integral converges. Again, if you have an integral of this sort, 1 over x dx, again, this is an improper integral because you have here integral from 1 to infinity. So what you do, again, you do the same thing from 1 to c, and you take the limit when c tends to infinity. But you found out a difference between this example and the previous one because your logarithm when c tends to infinity becomes infinity, and therefore your function, your improper integral diverges. For example, evaluate this integral here is the same, but here you have from minus infinity to infinity. Doesn't matter. You may decompose your interval from c1 to 0 and from 0 to c2, and then you take the limit when c1 tends to minus infinity and c2 tends to infinity in order to scan the whole domain. You can do this, or you may, as a matter of fact, since this function is even, you may consider twice the integral from 0 to infinity. It doesn't matter. The first one here, this is an elementary function in which the integral is equal, the antiderivative is directly the arctan of x, and from c1 to 0 you get it minus 10 minus 1 c1, and the other one is the same thing, 10 minus 1 c2. When you take the limit when c1 tends to minus infinity, you get here minus and minus pi by 2, so you get pi by 2 plus pi by 2, you get pi, and this is the value of your improper integral because it converges. Again, sometimes you are not interested in evaluating improper integrals. All you wish to know whether this integral converges or not. So here there is a test for convergence. For example, if you have two functions, f and j converges, then f converges. While if f diverges, j diverges. So for example, if you have, for example, and same thing, here is the result. If the first integral g of x dx from a to infinity is convergent, so does the integral of f of x. Whereas if f of x is the one which diverges, then so does the integral of g of x dx. For example, suppose you want to check for the convergence of this integral. You are not interested, in fact, of calculating the integral itself, just to know whether this integral exists or not. So all you have to do is that you can compare it with another integral, like for example 1 over x to the power 3 over 2. And this one converges. Why? Because you take the limit when c tends to infinity over the closed interval from 0 to c. You wish to first you calculate this integral from 0, which is 1 over square root of x, for example. And no, minus 3 over 2, so square root, you have minus 3 over 2 plus 1, which is minus half, 1 over square root, which is 1 over square root of x, and then you substitute from 1 to c, and then you take the limit when c tends to infinity, so it ends up to 2. This is the value of the integral, and it means that this integral converges. Since this integral converges, and you have that this function is less than this function, of course, because you have added up here 1, so it means that since this converges, this must converge. And here it is. This converges, and according to the theorem, this also, since it's smaller, must also converge. And of course, it's positive. The second type of improper integrals occurs when you have the region of integration is not closed unbounded, when the function itself is unbounded over, for example, a closed interval. Suppose, for example, you have a function like the integral of 1 over square root of x dx from 0 to 1. Same thing, you might have this, or you might also give it a value at 0 equal to 0. Again, the same thing. This is an improper integral since the function is unbounded over this interval. But if the integral exists, in other words, if you carry on the integration and you take the limit and you find that it exists, then your improper integral exists. Here, what you do is that you carry on your integration on the closed interval from c to 1 instead of 0 to 1 from c to 1. Now, from c to 1, this function is continuous, and therefore you can apply the fundamental theorem. Once you can do this and you find the value of your integral as the antiderivative substituted for at the two limits of your integration, then you may take the limit as c tends to 0 from the right hand side. If it exists, then your integral exists. For example, here 1 over square root of x dx from c to 1 is equal to 2 times 1 minus square root of c. Now I wish to obtain the improper integral, calculate the improper integral from 0 to 1. So what I do, I take the limit when c tends to 0 from the right hand side, and I find out that this tends to 0. I finally get to 2. In other words, your this improper integral in fact converges. For example, here, the integral from 0 to 1. This function, in fact, has as domain all values of x comprised between minus 1 and 1. So between minus 1 and 1, at 0 there is no problem. So it's at 1, as a matter of fact, which constitute the difficulty here. Because at 1 this tends to infinity. This is an improper integral because you have the value of 1, the function is unbounded. So all you have to do is that you take the integral from 0 to c. And after you take the integral from 0 to c, and c is less than 1, since the function now is bounded and continuous over the interval from 0 to c, you can evaluate it according to the fundamental theorem. And once you do this, you end up with what? You end up with the antiderivative, which is sine minus 1c. And you substitute from 0 to c in order to, and at sine minus 1, 0 is 0. So you get at the end sine minus 1c. And then finally, you take the limit when c tends to 1 from the left-hand side, because actually it's the left-hand side which now here is important because the function is defined from minus 1 to 1. So when you take the limit, if you find that it gives a result, it means that your integral exists and that your improper integral in fact converges. Now, here is some application of the integral. We've seen that the fundamental theorem, in fact, all you have to do is that it's very easy in applications. Why? Because all you have to do, it can calculate all sorts of things, areas, volumes, etc. The ideal is that to calculate the antiderivative of continuous functions. You know that it's continuous, or you impose a certain condition of continuity, and then you calculate the antiderivative, and then you substitute for the limits of integration. And once you do this, you have done some sort of applications. You have reached some sort of applications of the integral. So in fact, it's the fundamental theorem which plays the highest role, or the maximum, or the when we say the most important role in engineering, because you always use it all the time. In any field which you're going to study. So the application of the integral, in fact, either the fundamental theorem or whether your Riemann theorem, it's all the same. You have some sort of integrals that you wish to calculate. These integrals actually appear in all sorts of applications, in a variety of applications. You find your integrals, for example, when you wish to calculate areas of surfaces, domes, for example, areas of domes, etc. For example, they also appear in mechanics. They appear in material science. We've seen in mechanics, you wish to calculate, for example, the trajectory of your particle, for example, the distance at which it reaches. For example, you have a differential equation, you solve it, Newton law or whatever of gravitation, and you end up with a function as a distance, or a function in terms of t, and this function represents the velocity or the distance. So in fact, you are doing an application in mechanics, in material science, in hydrostatics. All you just name it. Any application in engineering, you have to use the fundamental theorem. So one of the actually important applications is the differential equation. This is in fact the second law of Newton. The second law, when you integrate it, you get y, which is the distance as a function of time. Again, in functional expansions, suppose for example you wish to sum up this series. It's difficult, but if you integrate it, for example, you end up with what? With geometric series, and you know the sum of geometric series. Here they have ratio 3x. All you have to do is to sum up this series, which you can do it very well from school. Once you do it, once you calculate the sum, you can differentiate it again to obtain the sum of the above series. Again, for calculating areas, in fact, you have to know something, that integrals can have a sign. The integral can be positive, can be negative. For example, here it's positive and here it's negative. So if you wish to integrate, for example, cosine x, the area, to calculate the area from 0 to 3 pi by 2, you don't say the area, you say the integral now. So the integral of cosine x dx from 0 to 3 pi by 2, the antiderivative is sine x, you substitute, you get minus 1. So minus 1 represent what? Represent the integral from 0 to 3 pi by 2. Whereas if you're interested in the area, then you have to revert the sign here. Here you have it positive, so you leave it as it is, whereas here, if it is negative, then you revert the sign. In other words, you do the integral in parts. The first part, for example, from 0 to pi by 2, you get 1, and from pi by 2 to 3 pi by 2, you get minus 2, so you have to revert the sign here. In other words, your area is equal to 3 units of area, whereas the integral is equal to minus 1. So, in fact, integrals are such that they can be of different signs, or of positive or negative sign, whereas areas always are positive. Of course, if the area lies between two curves like this, it's easy. Then your area in between is equal to what? The integral of f of x minus g of x. The area below the first one, subtract from it the area below the second one. Here it is. This is the law we're going to follow. Suppose, for example, you have two curves like this, y is equal to x squared and y is equal to x over 2, and you wish to calculate the area in between. All you do is that the integral of what? The upper one, which is the maximum y, the one which has the y, the maximum y, which is x plus 2, minus x squared. This is the ordinate y. You multiply the x plus 2 minus y squared, which is the height between the two curves, times delta x, and you integrate. In other words, this is the area between the two. Of course, you have to integrate between the points of intersection. In other words, you have to solve first the point of intersection between the two graphs, and then you carry on your integration in order to obtain the area between the two. Of course, you may your curve, your region may be like this. So either you take it when you solve for the point of intersection. Either you consider the first part here, which is the difference between the same graph when you solve for x square root of y and minus square root of y, or y is equal to square root of x and minus square root of x. And then plus the integral over the second portion here. In other words, as if you are drawing here a vertical line. But better than this is that you can follow a different line, a different course. Is that you can, in fact, take a horizontal lamina. In other words, you subtract x this from x this times dy this time. And so if this is higher, x here is greater, then you say that the area between the two is equal to y plus 2 minus y squared in this times dy. In this case, and you end up with the region, with the area between the two graphs. This is the first method, but in fact the second one is much easier. Now, if you have two curves like this, they intersect, and you wish to calculate the area between the two, of course, this is, if you put here y, here you calculate the area between, in the first portion here, which is the integral of f of x minus g of x, and this is positive this time because f is greater than j, whereas here j is greater. So what you do is that in order to calculate the whole area, you calculate from a to c, plus from c to b, but here you revert the sign of f of x minus g of x, and then you add up both areas together to obtain the area between the two graphs over the whole range. Here again, like for example, you have x squared and x cubed. X cubed is smaller from 0 to 1, whereas it's greater here from x squared. So all you have to do from 0 to 1, since x squared is greater, you calculate the integral from x squared minus x cubed, whereas from 1 to 2, you carry on the integral of x cubed minus x squared dx, and you finally end up with 3 over 2. And this is the area between the two graphs, whether it is in between from 0 to 1 or it is 1 or 2, and it is a unit of area that is the sum of both areas, in fact. Again, the integration may not be over x. You may not be using Cartesian coordinate, or you may not have a y as a function of x. You may have r as a function of theta. Here you have an r as a function of theta, and you may have a little piece here. This triangle here have as area half r squared delta theta. So in fact, instead of defining the integral as the integral of f of x dx, you may actually define it in this form here. And if you have r as a function of theta, like for example, you have an area of a cardioid. This is resemble your heart. So the area here is equal to what? Half r squared d theta, and r is equal to 1 plus cosine theta. And this is a kind of representation of graphs. It's called polar representation, and you don't have to work out with your Cartesian coordinates. Here they're called polar coordinates. You may, and this is directly the integral, how you do it. Suppose you have your function is given in a parametric form, and you have x is equal to function of t and y is equal to g of t. You may do it this way. Here you have it, the integral of f of x dx, and since f of x since you have x y, or in other words y dx, and y is equal to what? To g. So you have g of t times dx. What's the value of dx? F prime of t dt. So actually this is your integral in the parametric form. So for example, if you have a cycloid and you wish to calculate the area under the cycloid, all you have to do is you substitute in your expression you have seen before, and you carry on the integration. And all of these integrations are very simple. In fact, they're antiderivatives, and then you substitute 4 by the limits of integration. You may also have a lamina of this sort. If you have lamina of this sort and you wish to calculate the area of circle, for example, then you take a lamina. This thickness of the lamina is equal to what? Is equal to circumference 2 pi r at with radius r, and the thickness is equal to what? Delta r. And then you carry on the integration. And in fact, if you calculate this from 0 to a, you end up with pi a square. So in fact, this is another way of calculating integrals. You don't have, again, to use the form which is f of x dx, or the form which is f r squared d theta. You may not use neither Cartesian nor polar coordinates. All you have to do is to search for a region in which you can, if you extrapolate it, and in other words, if you obtain the sum of it, then you calculate the area under study. And here it is, pi a square. Again, you may have solids of revolution. Different integrals allows you to calculate solid of revolution. Suppose, for example, you have a half circle and this half circle rotates around the x-axis. What do you get? You get what? You get a sphere. Instead of showing it here, in fact, this sphere is each lamina, when it rotates, you obtain a volume of a cylinder. The cylinder is equal to what? Pi multiplied by y squared, which is the height, times the x. In fact, instead of showing it here, we might, in fact, show it here. Here you have your lamina, and all you have to do is that you discretize it in the form of this half in the form of laminas, each of base dx, and you let it rotate. You let it rotate around the x-axis. If you rotate it around the x-axis, what do you get? What do you get? You get a cylinder. This cylinder represents the piece of lamina, the piece of cylinder which is a part, as if you have a ball, a sphere, and then you cut it into pieces. Each piece is what? Each piece is a cylinder of radius dy, radius y, and of base dx, and therefore its volume is equal to pi y squared dx. This pi y squared dx, if you integrate it, if you accumulate it over the whole region, what you get something like this, a sphere which is cut into pieces. And then this sphere, when you take the limit, when n tends, number of subdivisions tends to infinity, you finally actually get your sphere. So your sphere, in fact, this is one application which is a volume of revolution of a certain region. This is one application of different integrals. So in fact, the disk technique runs as follows. You have a function f of x, and you wish to rotate the curve of this function, which is, for example, in this case, y is equal to square root of 1 minus x squared, rotating about the x-axis. So as I said, you have a lamina here, and this lamina, when it rotates about the x-axis, what it does represent? It does actually draw a cylinder, and the volume of this cylinder is equal to what? This is the radius, y, so it's equal to pi y squared times the height, which is dx. So when you accumulate all these sums, which is the summation of f of x times, f of x squared times pi, because this is the area of the base, pi f of x squared times dx, and you accumulated along all the intervals from -1 to 1, you get the volume of revolution, in fact. So the volume of the rotating disk becomes equal to the integral from -1 to 1 to pi times f of x to the square dx, and this is equal to 4 over 3 pi. And you know very well that this is the volume of circle of radius 1 and of center at the origin, and the volume is equal to 4 over 3 pi. Again, so in fact, this is your theorem. It tells you if f is continuous on the closed interval AB, the volume of the solid of revolution of the region bounded by y is equal to f of x, and the x-axis between a and b around this axis is given by. And this is the theorem. This is the integral which you are going to use. Given f of x, which is the function that you wish to rotate its curve about the x-axis, and this exists on one part of the x-axis, on one side of the x-axis. So in fact, your volume of revolution of the solid of revolution is equal to pi times the integral from a to b of f squared x dx. Again, suppose you have a region like this rotating above the x-axis and you wish to calculate the volume of its revolutions. What you do, it's simple. You have it as, for example, you consider it as two curves, f of x and g of x. For example, even if it is one curve and closed, you solve for y in terms of x, and then you calculate the volume of revolution of the first curve, which is f of x, around the x-axis, and you subtract from it the volume of the second curve around the x-axis. And this is your expression here. Again, there is other applications, of course, of integrals. For example, you may, for example, use it to calculate, for example, length between of a graph, length of a curve between 2 points. For example, you have 2 points A and B, and you wish to calculate the length. This length, how you do it? You take a little piece dl, and you, thanks to again to the differential of Leibniz of projection dx on the x-axis and dy on the y-axis, and from here directly you apply Pythagoras, you get dx square plus dy square, and therefore your dl is equal to what? The square root of dx square plus dy square, and you take dx square outside, so you have 1 plus d1 by dx all square dx. And this is in fact your differential or infinitesimal or differential of the length. In fact, this is if you wish to integrate, to calculate the length between the point A and B, all you have to do, you integrate from A and B. And this is actually the length between A and B. This actually can be of an application in calculating, for example, surface area of revolution. For example, here you wish to calculate the outer area, surface area, when this graph, for example, rotates about the x-axis. In which case, what you obtain? In fact, you obtain the outer surface area of a cylinder for each lamina that you consider. Suppose you consider this lamina. Here, it has as radius y, but the area, the surface area, the outer surface area of revolution is equal to what? Is equal, you know, the outer surface revolution of a cylinder is equal to 2 pi r times the height, if it is right cylinder, if not multiplied by the directress. So in fact here you have, since this is y, so you have 2 pi y, this is the circumference of the cylinder, times dl. But you know that dl is equal to the square root of 1 plus dy by dx to the square. So you end up actually with a formula of this sort. If f is differentiable on AB, the curve situated on one side of the x-axis, the surface area of revolution, in fact, of y is equal, of the curve y is equal to f of x, from x is equal to x to x equal b, is equal to what? 2 pi, the radius, which is f of x, times dl. But dl, we just showed that dl is equal to the square root of 1 plus dy by dx square, which is f prime square dx. So in fact, if you are given a curve of equation y is equal to f of x, all you have to do is that you substitute here and you calculate this your surface of revolution, and this gives you the surface of revolution around the x-axis. Suppose we wish to show this on our applets here. So suppose you want to obtain the outer surface area of a parabola when it rotates about the y-axis. So all you have to do is that you divide the region into horizontal lamina, and for each such region, when it rotates around the y-axis, what you get is a cylinder. In fact, the outer surface area that you see is equal to what? Is equal to twice pi the radius, which is x, times the length BC. And this length BC is calculated before as in fact the square root of 1 plus dy by dx all square times dx. So in fact you substitute in your law that we've just in your expression that we have just stated in our slide. And if you carry on this, you want to calculate all the surface area, or the whole surface area, outer surface area of your parabola, which when it rotates about the y-axis, all you have to do is to carry on your integration, all your summation over all the lamina. This is actually a corrugated surface, because you haven't got taken the limit when n tends to infinity. And when you number of subdivisions tends to infinity, or the dy tends to zero, what you get is your area. This is the surface area, in fact, that you wish to calculate. So going back to our slide, here is the law actually which we apply to obtain the surface area of revolution, as we said before. In fact, here, for example, suppose we wish to calculate the outer surface area of revolution of this half circle around the x-axis. What you get? You get the outer surface of a sphere, which is 4 pi r square, in this case 4 pi. Here you have your y, so you start to apply your theorem. First of all, you get dy by dx. After you get dy by dx, you directly substitute into your formula. It tells you what? The surface area of revolution is equal to 2 pi f of x, which is the square root of 1 minus x squared, times the square root of 1 plus dy by dx all square. Here is dy by dx. So when you square this, you substitute it here, and actually you find out that this cancels out, and you end up with 4 pi. So this is actually the surface area of your sphere, and it is known that it is 4 pi. In fact, there are other theorems for surface of revolution. This is not the only one. In fact, we can. This is in fact a method which is known after Pappus. Pappus is called Pappus of Alexandria, and he lived in the Bibliotheca of Alexandria. And the funny thing is that he devised a method by which one can easily calculate surface of revolution. For example, suppose you have, for example, an even volume of revolution. You have, for example, a curve like this, and you wish to calculate the surface of revolution around an axis. What you do? You try to calculate the center of gravity of this curve here. Suppose it is here, and then you multiply it by twice pi the radius of revolution around the axis. Again, if you have, for example, a region like this of any shape, and you wish to calculate the volume of its revolution around the y-axis, what you do is that you first of all you multiply the area by what? Here you multiply the length of this piece here, multiply by twice pi the radius of revolution. Here if you want the volume of revolution, it's funny, you multiply the area of this region, whatever shape it takes, multiplied by 2 pi r. What is r? Is radius of revolution of what? Of the center of gravity of this shaped region around this center of gravity, the distance between its center of gravity and the axis of revolution. So here, for example, you have a circle and you wish to rotate this circle around, here the circle in red, around the y-axis. So in fact you get a torus. This torus of volume is equal to what? Is equal to the area itself, the value of this area, times 2 pi r, and this r is what? The distance between the center of gravity of this circle, which is at the origin exactly, and the axis of revolution. So it's simple. A times 2 pi r, and I is the distance between the center of gravity and the circle of gravity of this shaped like figures are very well known. Of course, it's in the origin, and the axis of revolution. If you multiply them together, you get directly your volume of revolution. Again, suppose you have a line like this, and you wish to calculate the surface of revolution of this line around the y-axis. What you get? You get a cone. What's the value of this? The surface area, the outer surface area of this cone is equal to the length of this line times 2 pi r, and r is the distance between its center of gravity and the axis of revolution. And here it is. So we see, in fact, that Pappus, although he lived at the time of the Library of Alexandria, before Christ, in fact, he was able to present a theory which actually could not be known unless with the advent of calculus. So to this end, in fact, we came to the end of our lecture, and we in this lecture actually we have displayed, we explained the fundamental theorem with all its applications. There are so many applications, in fact a multitude of variety of applications, not only the one that we displayed here, but other as well. To the end of this lesson, and this actually complete our lessons in our series of lessons about calculus, and I wish to remind you that all these lessons are uploaded to the site of the MedNet-U. In fact, I wish you good luck, and I hope you really benefited from all these lessons I presented to you, which I've been prepared thoroughly. And I wish you really good luck in your study pursuit. And finally, I thank you very much for your attention and for attending these lectures. Until we meet again, thank you very much.